Alright, so welcome to the second video. In this video, we're going to cover a transfer function that crosses the imaginary axis. So my last video was, I think, it was too long for a simple root locus problem. So in this one, I've decided to write a bunch of them beforehand, and I'll just explain as I go through them. So we have this, we are given this loop transfer function, GC of s, and we are asked to draw the root locus. So I wrote down all the 6 steps that you have to take in order to draw them. So the first step was to find the poles and zeros and number of asymptotes, which we did. So we said that we have 3 poles, one at 0, one at -5, one at -20. Okay, so I wrote them here. And then we have no zeros, so zeros is just nothing. And then the number of asymptotes was just n minus m, so number of poles minus number of zeros, which is just 3. And then, so that's the first step done. And then the second step was to find the angle of these asymptotes. And we used this same formula. And because we have 3 asymptotes, we do this equation 3 times. And the first is to set q equals 0, and then 1, and then 2. And if we had, let's say, if we had, instead of this, let's say we had 5 asymptotes, right? We would just do this equation 5 times, starting from q0 up to q4, because 0, 1, 2, 3, 4, see, it's 1, 2, 3, 4, 5. Okay, I hope we get that. So we did that, and then we found out that the first angle is at 60 degrees, the second angle is 180, and the third angle is at 300, which is just another way of saying -60. So the second step is done. The third step is to find the centroid, and this is the formula for centroid as we discussed earlier, and we did that and we got this. Okay, so this is the centroid. Just to remind you, this is where the 3 angles go. Okay, so that's where we draw the 3 angles. And if you just quickly draw this, it's gonna look something like this. Okay, let's say this is 2, 4, 6, 8, 10, and then let's say this is -8.33. Okay, so this is a centroid. This is where we draw a 60 degree, a -60 degree, sorry, a -60 degree, and then a 180 degree. Okay, so that's where we draw the 3 angles at the centroid. Don't forget that, it's always the same. Okay, and the fourth step is to find the break-in breakaway points. And just like before, as I said, this is the same formula for even a very complicated transfer function. So we write down this one except the k. So 1 over s plus 5s plus 20, because coefficient as k is just 1, right? You just don't write it, so it's just 1. And we write the same derivative technique as uv. So I said, it's if you have a equation uv, its derivative is just u prime v minus u v prime over v square equals 0. Because this multiplies with that becomes 0, so instead of writing all of that, we just write this. Okay, if you just write this, it's gonna save you a lot of time. So all we're concerned about is doing this. Okay, so all right, so using the same technique as before, we found out that this is what we have, right? So we get that, and then we multiply this thing with 1 over 3 to get rid of this 3 coefficient, and then we obtain this equation, and we can just use simply quadratic equation to find the 2 roots, s1 and s2. So it gave us a -2 and -14. Now it shows us that we have 2 breakpoints, but at this time you can just draw a basic root locus to determine if both of them are eligible or just one of them. Okay, so you can just quickly, just draw this. It's useful for you. So we have 3 poles at 0, right? Let's say this is -5, and let's say this is -20. And we have no zeros. Okay, so the way that drawing this stuff works, you obviously have to draw this, right, the centroid, because it's your asymptotes. So if that's a -5, this is your centroid at -3, okay? And the way it usually works, right, so you only have 3 points. They're all on the real axis. So you always, okay, you draw these two, you always start from the right going to the left, and then you try to make connections. So this, and then you leave an empty space, and then you continue drawing again. All right, so you do that, and then you draw your centroid, right, which had a 60, -60, and a 180. Okay, this red part is your locus, at least for now, because we don't know a lot. We just know that these violet color, they represent your asymptotes, okay? So don't confuse it with the locus. They represent your asymptote. And we can see that -2.32 and -14. So we know that this is a 5, this is a 0, this is a -20. So from the locus shown on the red, we can see that -2.32 lies on the locus, okay? So this is -2.32. This point lies on the locus, but -14 is somewhere in here, right? It's let's say this is -14. It does not lie on the locus. So the locus, so we just disregard this value, okay? So the only thing that we take into account is just -2.3. That's it. This is our only breakaway point at -2.3. All right, so we've done, okay, so far we've done this, we did this, we did this, we did this. Now we have to determine where it crosses the imaginary axis. And we have to take the characteristic equation, which I'm going to write based on what we have here. Okay, so this is the characteristic equation that we are going to use to find where this locus crosses the imaginary axis. So far from the angle of asymptotes, we have an idea, okay? We have a rough idea that, let's take a look at this breakpoint, okay? Because breakpoint is where your locus starts, starts to grow. I guess I could say that, where it starts to move, I think. So the locus lies at this point, okay, -2.32. And we have a rough idea that the locus is gonna go something like this, okay? Because of this this asymptote angle, okay? So the locus is gonna go like this. Actually, I should write it in red because it's part of the locus, okay? So far you have a rough idea of your root locus, and you can see here, right, that it crosses the imaginary axis, as we said that this is the imaginary axis and this is the real axis. So it crosses the imaginary axis. We have to find where it crosses the imaginary axis, and we have to find that point. What is that, right? What is that point that crosses the imaginary axis? And as we know that the complex numbers, they're always complex conjugate of each other. So let's say from this equation we find that S is let's say it's 0 plus minus I don't know, let's call it 2, okay, 2j. It just means that this is 2j and then this here is -2j, okay? That's just the basic idea, okay? And now we are gonna actually solve it, and we solve it using this guy's method, okay? So s cube is square, s1 is 0. So we write it this way. assuming that you're here to watch how to draw the root locus, you're already familiar with Routh-Hurwitz method of finding a system, of checking for system stability and for root locus. But I think it's safe to say that let's just let this be a refresher, okay? So we have this characteristic equation, okay, equals 0. So for S cube, right, the first one, we take this, escape 1, take 1, escape 1, take another. So we only take this and this. Oh, I apologize, it's 100s plus k. And so we take 1, escape 1, take 1, escape 1, and then nothing. So we just write coefficient of S cube is 1, coefficient of S is 100. That's for S cube. Now for the S square, we escape that one, we escape this one, okay? So we take 1, escape 1, take 1. So we have 25 and k. Okay, so we draw for these two. Now what do we write for S1? Well, S1, let's call this alpha, and for S0 is just k. Alright, so that is just k because it represents the last one. So for alpha, what is alpha? Alpha is 25 times 100 minus k divided by 25. Okay, it's basically this multiplied by that, right, minus this multiply by that, minus k, and then divide by this value, 25. That's just the basic for that method. So from here we find k, right, which is just 100 minus k over 25. So that's our alpha. And now, now that we have alpha, we if we try to find this, is nothing, it's just 0, because beta, to find beta, we have to have a value here and here, okay? And because these two are just 0, our beta would be 25 times 0 minus 1 minus k times 0 divided by k, right? Which is just 0 times 0 is just 0. So that's why we don't even write beta, because we know it's 0. So we know our value for alpha. Now we have to find k. And why do we find k? Because we have to determine the system stability, or marginally stable is when a system is marginally stable when it crosses when the locus crosses the imaginary axis. So 100 minus k over 25 equals 0, right? So 100 over equals k over 25, and k equals 2500. So it just means that when k is 2500, we have the system is stable. Now using this k value, we consider this row, okay? We consider this row to find the imaginary axis. So 25 is square plus k equals 0. All right, and we know that k is 2500, so it's gonna be 25 s squared equals negative 2500. All right, and so that divided by that gives me a s value of plus minus 9.99 j. Apologies, it's just 10. So now we know that the root locus crosses the imaginary axis at plus minus 10 in the imaginary axis, like we said earlier. So now let's draw the actual root locus, okay? So we draw the right, so we draw the axis first, sigma real axis, and JW imaginary axis. We said that we have 3 poles at 0. Okay, we have poles at 0, and we have another pole at -5. 1, 2, 3, 4, 5, and then another one at -20. Let's just call this 20. Doesn't matter. Okay. Well, it does matter, but for our case, not really, because the breakpoint is in between here. So that's what we are concerned about. And let's see our centroid. So our centroid is at -8.33. All right. All right. So I wrote down everything that we need to draw this root locus. So we can see the poles at 0, -5, and -20. We can see the centroid at -8.33, and we can see where I marked the imaginary crossing at ±10j, and the angles which I've drawn here. Okay, so 60 and -60 and 180, right, which is just the angle here. You get the idea. Okay, and now let's get to drawing the locus. Okay, so we always draw like this. Okay, so first let's draw the general locus. Okay, so it's gonna start from here, go up to here, and then leave this empty space, and then it's gonna go here. All right, so that's like the general idea on writing the locus. Now we can see that we have a breakaway point, and that the locus will go from here, cross here, and then continue with respect to this asymptote. Okay, both ways. So now we're gonna draw like this. All right, so something like that. All right, and it's gonna go both ways. All right, I'm not good at drawing, but if you use a software, it's gonna make things much easier to understand. So that's our like a general look on the root locus. Now let's get specific. Okay, so to get specific, let's so we know that this locus starts from here. Oops. All right, so okay, so let's call this, it goes from here up to the breakpoint. All right, and now goes up to the breakpoint, and now it's gonna go down like this. Crosses the imaginary. All right, yeah, and the another one, it starts from -5, goes up to the breakpoint, and then it shoots upward. Okay, +10j, and then it keeps going with respect to this asymptote angle. And our last one is just this other one, which starts at -20 and then goes up to the infinity. All right, so this is it. This is your root locus for an imaginary axis, and again, it has no departure or arrival angle because we have no imaginary pole or 0. So thank you for watching, and see you in the next one.